Hi everyone, in my first review you saw how the Creality Pika performs. Today I show you the proper way to use it, covering its different scanning modes, a blue laser with markers, a marker-free laser, NIR mode, and phone-based scanning. In the second part of the video, I will show you the complete workflow of reverse engineering this part using 3D scan data from the Pika in BricsCAD, followed by a test print to check if the print part fits correctly. The Pika can't draw power directly from your computer's USB-C port, so you will always need to insert a battery to run it. There is a toggle switch here for Wi-Fi and USB, and you need to set it before powering on the scanner. I'll kick things off in laser mode by connecting the scanner to my PC with a USB-C cable. The Pika offers two scanning modes, laser line and infrared. The laser line delivers the highest quality and most accurate results, but it does require markers to track its position relative to the object. It's not always necessary to stick the marker dots directly onto the object. You can place the sticker markers on the bundle turntable and then set the object on top. The smaller 6mm markers are designed for narrow or curved surfaces. The 10mm markers deliver higher accuracy and more reliable tracking performance. Place the 10mm markers on the turntable, spacing them about 5 cm apart. The object on the turntable must stay completely static relative to the markers. If the markers move, the object has to move with them, because even slight vibrations will affect scan quality. You shouldn't place any extra markers outside the turntable since they won't moving together with the rest and will disrupt tracking. I recommend raising the object on the turntable by about 10 to 15 mm. This can help capture the sidewalls more effectively in some cases. The Pika doesn't work with my front panel USB-C port, but it does run fine when plugged into the rear port that connects directly to the motherboard. To use the Pika, you will need to download and install Creality Scan version 4.3 or later. I will include the download link in the description. Before creating a new project, set the default save location from the setting menu. Then click on the new project. You can also include the space in the project name. When connected by cable, you have two tracking options, with markers or without markers. I will choose with marker on the first demonstration. Next, you will need to set the proper scanning resolution. This is the most common mistake new users run into. Scanning resolution refers to the spacing between points in the point cloud generated by the software. For example, if you set the resolution to 0.15 mm, the distance between each point will be 0.15 mm. Resolution doesn't affect the accuracy of the scan data, but it does determine how much detail the scanner can capture. For a card trim of this size, I've set the resolution to 0.2 mm. This one is also set to 0.2 mm because the clips have fine details that need to be captured. It's best to set the scanner to the lowest resolution that still shows the detail clearly. You can run a quick test scan on a high detail area to determine the proper resolution. For smaller trim like this, I set the resolution to 0.15 mm. It's compact and capturing won't take much time. For this door handle, I set the resolution to at least 0.15 mm. It has a very small clips and 0.2 mm would be too wide to capture them properly. For scanning efficiency, I set it to fast since I'm working on a high performance PC. Now I point the scanner toward the object and it will automatically detect the scanning range and move it closer or further until the laser line appears clearly on the surface. Then click the start button. I'll leave the IR camera exposure set to automatic. When the object is smaller than the turntable and doesn't fully block the markers, as long as the scanner detects more than 4 markers, it will keep tracking. In the upper left corner, you will see the frame count, which is capped at 60,000 frames. Setting a higher resolution makes capture take longer, increase the frame count, and can introduce unnecessary accuracy error. It also generates excessive scan data that can weigh down your PC's performance. In cable mode, the Pika runs at 120 frames per second, more than twice the speed of the Raptors. After finishing the scan, click the Finish button. This will take you to the Project tab. Next, I will flip the object to scan the bottom side and then align it with the first scan. Soon you will notice that the included turntable doesn't rotate smoothly, and the uneven motion can create vibrations while turning. I recommend using a turntable with a good quality ball bearings like this one. I made a DIY video about it last year. It's 35 cm in diameter, and about 80% of my scanning projects can be done on it without wasting sticker markers on the object itself. This turntable also has marker placed at the extreme edge, a tilt at 60-degree angle. That design helps the scanner maintain tracking when scanning taller objects. I also built a version for 26 cm build plate printer, but not for 22 cm. That size too small and would require too many joints. Click the new scan to create another scan within the same project. Remember, multiple scans must be in the same project in order to be aligned. The Pika uses narrower lenses than the Smooth series, which allow it to fully capture slots and gaps without leaving blind spots. It won't go deep into holes, but the scanner still provides enough data for reverse engineering. I will demonstrate it real performance in the second part of the video. After stopping the scan, click Finish. This will return you to the same project tab. Turn on the visibility of one scan dataset so you can identify and remove the unwanted data. Now you can power off the scanner to save battery. Click the clipping plane button, then left click to select 3 marker dots on the turntable. This creates a cutting plane that erases everything below it. For the remaining areas, use the lasso tool to select and delete them. Click Save to keep the change. Next, I click on the second scan. It will automatically toggle off the first scan. Similarly, I use the lasso tool to remove the pyramid support. Pick the object you want, hit invert selection, and it will highlight everything else so you can delete the excess. Hold the Ctrl key and select both scans. Click on the Fusion tab. Adjust the Fusion resolution so it equals the real-time resolution. Here that's 0.15 mm. Noise removal stays at 30% by default. Fusion brings out all the detail, but you will likely need to clean up extra data once more. Select the single body, click invert selection, and the rest will be wiped out instantly. Single body, invert selection, delete, and then save. You can also rename the scan dataset within the project. Before starting the alignment, make sure all unnecessary data has been removed. It's totally fine if you miss a few spots. You can always remove them after alignment. Now click on the Alignment tab. You can try automatic alignment. It sometimes works if there's enough overlap area, but not with this scan. Click the Reset button, then open the Manual Alignment tab. The first scan is in the fixed window. Hold Shift and right-click to orbit both scans until their orientation match. Pick 3 pairs of reference points. They don't need to be perfectly precise, just enough to give the software a guideline. It will then apply curve fitting and align them automatically. Not all laser scanners can do this. Without successful alignment, reversing the scan data simply isn't possible. Next, click on Apply. The scans are aligned but still separate. Run the mesh function to fuse them together. For the best result, set the triangle value to match this number. The unit is in millions. Click Apply. No further settings are required. You will notice the number of faces is lower than the set value of 1.2 million. That's because the overlapping area have been fused. Now I have a completely clean, noise-free scan from Pika ready for export. Since I only use point clouds for reverse engineering, I will export the scan as an ASC file format. But if you plan to use it for other purposes, you can export the file as an OBJ or STL mesh. When you open the Mesh Processing tab, the first two functions, Simplify and Smooth, I never use as they reduce accuracy. For reverse engineering, I skip hole filling. It builds artificial surfaces, and I would rather recreate the model with a few blind spots than rely on something that isn't real. But if you want to do direct printing from scan data, the hole filling function becomes useful. You can repair the mesh model using the clay tool. Next is the Transform tab, which lets you rotate the scan data relative to the origin plane. I never use this function though it isn't precise enough for reverse engineering work. Next is the Quick Measure function. This tool doesn't work properly. The software can't snap the mouse pointer onto the point cloud, making the readout inaccurate. Even if it did work, I wouldn't use it. You can't precisely measure the distance between 2 points on the model without slicing it into thin sections. Normally, I just exit the software once meshing is complete. Next, let's move on to the wireless scanning. You'll find the Wi-Fi hotspot password display here on this page. With the new firmware update, Pika now lets you connect to a LAN network while still using the Pika Wi-Fi hotspot. Click the refresh button and it will detect the Pika. When the Pika shows up, click on it and enter the Wi-Fi password. Wait a few seconds and the scanner will connect. With a Wi-Fi connection, Pika scans at 60 frames per second, which is considerably fast, though not as fast as the Smooth P1, which reached 80 frames per second. Because of its smaller size, connecting a cable adds extra weight to the scanner. Wireless is my preferred choice. It doesn't feel any slower than using a cable, and as you will see in the comparison results, it doesn't sacrifice scan quality either. And next, let's move on to infrared scanning, which allows objects to be scanned without using markers. I set the scan object to normal, and for the size I will choose small. There is also a sizing guideline available here. For the tracking mode, I will choose texture since it uses the color texture to assist with tracking. Infrared mode doesn't have a resolution setting, and the preview screen will look rougher compared to laser mode. This mode tracks the object using its geometry, and it relies on near-infrared pattern projector, so the light is invisible. The tracking performance relies entirely on the object's geometry. On the front side of the handlebar, the curvatures provide enough detail for it to track normally. Now moving on to the back side. On the preview screen, you will notice the object wiggling. That's a clear sign of poor tracking performance. The backside of the handlebar doesn't have as many features as the front. To resolve this issue, you need to add more tracking features into the scene. Now the scan has stabilized and tracking is smooth. You should note that geometric tracking produces unpredictable results. Accuracy depends entirely on the object shape, and accuracy error cannot be determined. So only use geometric tracking when absolutely necessary, as it consistently underperforms compared to laser scanning. There are some situations where infrared scanning can be handy. For example, a quick scan in places where sticker markers can be applied. Because it's lightweight, wireless, and compact, you can mount it on a selfie stick to scan the underside of a car or other hard-to-reach areas for quick measurements. With infrared mode, you can set the output resolution during fusion. Here I will set it to 0.15mm, but in practice it can't actually deliver detail at that resolution. But it still provides enough precision to align the scans together. I compare the scan data with results from other scanning modes. Let's move on to markerless laser scanning. In this mode, you will need to connect the scanner using a USB-C cable. Select without markers as the tracking mode. Then click on apply. And it will prompt you to remove the infrared filter. In this mode, both the infrared and laser projectors emit simultaneously. In this mode, the data feels slower to capture, even though it scans at the same 30 fps as the infrared mode. Each frame is processed more slowly. It uses infrared to track geometry and a laser line to capture the point cloud. This gives higher resolution than infrared alone, but still lower than laser scanning with markers. Accuracy is also unpredictable, unlike with sticker markers where you consistently achieve under 50 micron error regardless of object shape. Geometry tracking doesn't guarantee that level of precision. This mode serves no real purpose for engineering applications. However, it attracts buyers since most tend to pay more attention to scanners that advertise this feature. With today's technology, there is no substitute for precision 3D scanning other than laser scanning with markers. Anyone frustrated with markers should remember the $78,000 Romer Absolute Arm. This was the standard tool engineers used before marker-assist laser line scanning arrived 2 decades ago. And here is the scan result from that scanner. A customer sent it to me for reverse engineering, but I had to turn the project down because the data contained too many blind spots and missing area. On the back side, all the clips are missing. In fact, you can get far more usable scan data from the 629 Pika when scanning with markers. During fusion, the maximum resolution in this mode is capped at 0.2mm. That means you never achieve the same quality as scanning with the markers. It still maintains good precision and the scans align successfully. And for those curious about how the Pika performs on larger trims, let's find out. The markers were positioned for cross-line laser scanning, so they were spaced further apart. The marker spacing designed for cross-line scanners like the Raptor Pro or Moon series is too wide for the Pika. It struggles in certain areas, and while adding more markers easily resolve the issue, it also means extra time spent removing them afterward. So larger trims doesn't pose a problem for the Pika as long as you provide enough markers. Next, I will switch to wireless mode for mobile scanning. Connect your phone to Pika hotspot, then launch the Creality Scan app. Wait until the connection is established, then click on New Project. There is a setting here where you can set the resolution same as when you scan on the PC. I choose 0.15mm for the resolution. Scanning on an Android phone works exactly the same as on a PC, though it runs a bit slower at around 40 FPS. I can't confirm this myself, but someone at Creality mentioned it should run at 60 FPS on an iPad Pro M4 with 16GB of RAM. And the phone I'm using is Snapdragon 8 Gen 5 device with 16GB of RAM as well. Mobile scanning on a phone is a very practical feature. You don't need a gaming laptop anymore. The scan quality is slightly different compared to a PC, but accuracy and precision has improved significantly since my test a few months ago. The workflow is identical to the PC version. You can add a new scan within the same project. With this new firmware update, you no longer need to disable mobile data to connect to the Pika hotspot, and scanning works without an internet connection on both the PC and the mobile app. You can also connect the Pika to an Android phone using a USB-C cable. But the scanning speed still tops out at 40 FPS, so for me, there is no real benefit in using that method. On the mobile app, you get the same tools: erase unwanted data, fusing point clouds, and even align scans. I must have forgotten to turn on the camera during the alignment, but the workflow is identical to the PC version. And here is the Fusion tab. And here's the matching process. And here's the align and mesh result directly on the phone. However, you can't export STL or OBJ mesh files from the phone itself. You need to transfer the project to the PC app to export. Mesh export works on the Samsung P1, but not on the Pika. Connect your phone and PC to the same Wi-Fi network. Then click Export on the phone. It will prompt you to scan the QR code. Once the file transfer is complete, you can view and export your scan data from the PC app. Let's compare the scan results across the different modes. I have also included the Samsung P1 in this comparison. Looking at the embossed text, the Samsung P1 delivers noticeably higher detail, followed by the Pika on PC, both wired and wireless. On phone mode, the scan delivers slightly lower detail compared to the PC. There is no noticeable variation between wired and wireless connection on the PC. The results are essentially the same. Markerless laser scanning gives better results than NIR, but the resolution is still noticeably lower compared to marker-based scanning. In conclusion, laser scanning consistently delivers the best results. Use this mode whenever possible. NIR, however, is handy for quick scans and for hard-to-reach areas. Let's move on to reverse engineering. The first step is figuring out how this part was originally modeled. I use a flashlight to highlight the edges. Here in BricsCAD, I have already made a video showing how to import point clouds, set up the user interface, and align the data. If you'd like to follow along, I will include the code file download link in the description. I also need to find a way to compensate for the time I spent producing these tutorials. After importing the point cloud, I create two lines. The longer one is for a cropping reference. The shorter one is for the mirror axis. Then I crop the point cloud into a thin slice, looking at the bottom view. Then I use the polyline command to create a segment. Then I hover over the lines and use the add bounce command to create a curve. And I will only model just one half of the handlebar. I also want you to notice how I orient the XY plane. In BricsCAD, you can only sketch on the XY plane. Now I'm preparing for the second cross section. I'll try to simplify the model. Some of the cut I will do it later after I finish the modeling of the main part. Most engineers, when they design things, they will start with the basic shape, but this part looks complex. It's because it has been around, it has been cut so many times. So reverse engineering is the process where you find the original modeling sequence of the designer. So you need to figure that out before you start modeling. Next, I turn on the selection mode and create the region. I use the UCS Z-axis and create a spline and tracing the curve of the original design. The curve on the top is a bit of the guessing work because the surface it has been cut out, so you have to do the assumption for the curve. Okay, this should be enough to create a loft using the rails. Here's the first segment of the solid. I'm creating the third cross section, and this is the scan data from the Pika. Here's the mirror axis. I will use the polyline to create the curve. Then I use the add bulge command to convert the straight line into arc. And I move the vertex to make it tangent, toggle on the point cloud so that I can plan for placing the guide rails. Here's the guide rail on the top. I use the spline with the 3 nodes. The one in the bottom appears to be just a straight line. And I also need another one here to lock the shape. Now I create a region first, because if I don't use the region, the sketch will be consumed after the loft command. Okay, this is the second loft. Now I'm applying the rails. You can see that I don't use too many rails. Next, I will union the two bodies together so that I can apply a fillet. Make the corner round. I will use the fillet command to smooth out the sharp edges that was created by the guide rails. Add more fillet here, and one more here, and one more here, and this edge as well. So now it looks very round and smooth. And there's one edge left in the bottom. I use a push-pull command to extend the tip of the handlebar so I can trim it. I create a polyline that I will use for cutting. Then I use the surface extrude command. Then I use the slice command and use that surface as a cutting tool. Then I use the fillet to round the edge. Next, I will create a cutout for the grip access. This cut is obviously made with the loft command. It has a taper cut, and here's the second loft body that I'll use for cutting. First, I'll create a cutting profile using the polyline, and then I turn it into curve using the add bulge command. See, this add bulge command is very quick to create a smooth curve. Then I copy the profiles here. Because I'm going to align and scale it, I use the align command to snap it onto these 2 points and scale it. I do the same for the section below. Use the align command to scale it. So I have 3 cross sections. Now I'm creating the regions so that the sketch won't be consumed when I loft it. If I loft 3 cross sections in one pass, it's going to create a curve, but I don't think it's the right curve. So I'll create 2 lofts with no curve, and I think this is the right one. Then I use the subtract command to subtract this. Now I have a cutout for the finger groove. Then I use the fillet command to round the edges. There is another cutout at the front of the handle. I think it's for aesthetic. So I will create the cutting surface. I'll use the edge surface command to extrude the polylines up to this point. I use the slice command to trim the solid with the surface that I just created. So now I have the required shape. So when you do the reverse engineering, do not jump into details. Those design engineers who originally designed this part, they are 9 to 5 workers. Nobody wants to complicate things. And reverse engineering sometimes can be harder than design the part originally, because you need to follow the shape that has been round, has been cut. Sometimes it's hard to guess what is the process of making this shape. I use the 3D mirror command to mirror the solid to the other side. Then use the union command to join them together. Turn the point cloud back on and you can see the precision of the Pika. The left and the right side of the model match the point cloud. Okay, next I'm going to model the bracket. I'm using the polylines to trace for it. Even in the curved area, I use the straight polylines. Then I later use the add bounce command and convert the straight lines into curve. And I move the vertex to make it tangent. Okay, let's mirror it. Okay, you can see that it matched the left and the right side. The Pika can really be used for reverse engineering. If you are using the river point scanner, you hit the wall at this point. The left and the right side of the mirror axis won't aligned. When I use the extrude command to extrude it, I just realized that this bracket is actually lean in one angle. So I create a sweep rails because I don't want to redraw the cross section again. I use the sweep command and this rail and push pull command to extend this face downward, sink into the main body. Okay, there is another indent here that need to be cut out. Okay, here's add bounce command. Slide the vertex to make it tangent. It's created from a different plane, so I use the extrude command to cut it. Actually, I need to cut it both way. And let me do the second cut here. Okay. I also need to trim this. I'm using the polylines with this shape. Extrude surface. Then use the slice command to cut it. Okay, let's turn on the shading mode. Looking for the abnormality. Okay, I need to do the chamfer with the unequal length. Okay, one more here on this side with the same value. And this is the hole that is incomplete from the scanning, but it gives me enough trace to get the cutting axis. You can clearly see the cutting axis when viewing with the point clouds. Next, I create a plane on the tip of the axis. Use the 3-point arcs to locate the center of the hole. Then extrude and cut it from the main body. Next, I will create a counterbore, but the center is not round. I share the same center at a smaller hole and extrude it. Using the point cloud as a reference, I can clearly see it where it ends and cut it from the main body. And that's it. The handlebar reverse engineered from the Pika. Next, I will export as the step file. As I said before, CAD file has unlimited resolution. It's unlike the mesh. There is no number of faces. It was created by mathematical equation. Here in the slicer, I need to find the proper orientation. I'll try this first. I should have printed this with the laser printer because it can produce much higher resolution than the FDM printer, 20 microns, while the FDM printer can do like 200 micron of the Okay, let's send it to the printer. I'm gonna print it with a PLA because I'm not going to actually use it. But if you really need to use it, you probably need to print with the ABS. The printing time is about an hour. And here's the printing result. Nothing to write home about. A few defects here and there from the printing. Okay, let's put in the color. Okay, it's fit perfectly. Okay, let's put it into the pot. I didn't use the vernier caliper along the process. The Pika can entirely replace the vernier caliper, the good one. Alright, thanks you guys for watching. I'll see you in the next video.